Okay, thank you for bearing with me and coming over here to the corner where we do the board work. But we're going to be doing the Carnot Cycle today, and I wanted to do the whole thing by hand so it slows me down and you can catch where you might make mistakes, and if you catch any of my mistakes, there's stickers on the line, and so we got to make sure we do it all correctly. But also, you kind of see the flow of the problem better when I do it by hand, and then we'll be capturing it on video too so that you can follow along later. But I wanted to squeeze everybody over here so that we're kind of right in front of where the board work's going to be done instead of trying to stare clear across the classroom. So let's get started on the Carnot cycle. This is the classic thermodynamic problem in CHEM, and as we said, it's sort of the best case scenario because all four legs of the cycle are reversible. I apologize for my voice. I'm starting to get a cold, so bear with me. And so the first thing to do in any of these problems is to try to set up the state variables table. The reason we spent the whole last lecture on adiabatic relationships is because you need those relationships to set up the state variables table. And so in connecting volume A to volume B or B to C, you have an adiabatic relationship. And so you need to know something about the working fluid of the engine. Is it steam, in which case you've got a nonlinear molecule and you'll have a different gamma? Or is it something like nitrogen and oxygen, which we're going to use today, just linear molecules, to drive our Carnot cycle? And so there we would have just 5/2 R for the CV and 7/2 for the CP. So this is the state variables table filled out in terms of equations, and then also the relationships that were typically given with motors, like the compression ratio and the displacement volume. And so for today's problem, I'd like to work with this printout from the Trans Am engine modification site. I mean, Trans Am really doesn't have any emotional connection to you, but that was the coolest car on the road when I was in high school. So I was looking for stats on machines and motors and cars, and I saw this Trans Am site. I was like, the Trans Am. It was so funny. We had this sweet little substitute teacher, Mrs. Sanchez, and she was just looked like the little grandmother on Sylvester and Tweety. That's exactly what she looked like. And then after school, we saw her go out into the front of the school and get into this beautiful white Trans Am with red interior. We're like, Mrs. Sanchez. She had the coolest car. So here's the Trans Am thing. We have a 400 cubic inch displacement and the compression ratio of 8.38. And so that with that information, we'll be able to get, which we converted to liters, the volume A, which is the smallest volume, and volume C, which is the largest volume. And so we can get volume A and volume C from the displacement and the compression ratio, and then we have to make some assumptions in terms of temperatures. Now I've gone through and done this problem in a spreadsheet and looked at essentially moderate efficiencies that we would get out of a gasoline car. So these temperatures work in terms of the efficiency of a gasoline engine. I'm not sure that these are the right temperatures. So the temperatures, the question I had was still open in my mind. I don't know what reasonable temperatures are for the gases in an internal combustion engine. So that's what I said is on the line. If you can Google that and do your research on that and inform the class, then I'll definitely be in your debt. Now, in terms of number of moles of gas, it's roughly, in the millimolar range, like 50 millimoles. It's not a lot of gas going in there. When we burn it, it produces an enormous amount of pressure. And so this is per cylinder. So, as we do the cycle, we're going through 8 of those. And then you have 8 of those times how many RPMs. And so you could calculate horsepower and those kinds of things once you do the cycle. But let's not go that far. Let's just focus on the Carnot cycle and getting the amount of heat put in and the amount of work that we get out of it. And so these are the various relationships. From AB, we have an isothermal expansion, and BC is an adiabatic expansion. And then we reset the cycle by doing an isothermal compression. That's CD, and then DA is an adiabatic compression. So we have different work equations and heat equations for the different pieces of the cycle. Come over to the left side, yes. And then the efficiency, we're gonna calculate the efficiency with the work and the heat, and then we'll also calculate the efficiency using the temperature. So there's two ways to calculate the efficiency, and they should match. If they don't match, that means something's probably off in your parameters. You haven't calculated the correct work, or you've made a mistake. The efficiency calculated with the temperatures can be used to check all of your other work. So are there any questions on the adiabatic cycle before we actually dive into the problem? One thing that I've noticed that students mess up on is they won't get these things identified correctly. So they won't recognize that this is the adiabats here. The adiabats are see, I screwed it up already. Let me go back down there and get my eraser. You can tell the cold medicine's having an effect. Okay, and so the adiabats are BC. Why is it not? Oh my goodness. There we go. Now we're ready. So the adiabats are B and C and A and D, and the isotherms are here and there. So they're opposite of each other. The adiabats are steeper than the isotherms. So you can remember they're opposite of each other, and the steepest ones are the adiabatic compression and expansion.
Well, the example you give on the example you give on will look like this, because the Excel one looked a little like.
Yeah, it may be shifted like that because that's realistic. Yeah, so some of the ones are really steep. So you might see one that looks like this, where this A to D is very steep, and you might not be able to tell where they swap. That's a terrible one. That's why I use Excel. Golly, that's just terrible. But yes, it could be steeper and it could look, confusing. But you should have little points on there where A, B, C, and D are. The other thing that's nice about the plots is if there's numbers on there, and I typically give you one that's generated by Excel on the exam, so you can check your work to see if it's feasible. Okay, by looking at the plot. So if you've got A and C are, say, 1 liter, and C is, say, 12 liters. So those are your full, range of volumes. And you do a volume in the state variables table, and you get half a liter for some volume. That's not even between A and C. So you know that you've got something screwed up. Or if you get something that's 15 liters, and that's beyond VC, and you're calculating VB or VD, you know you've messed up because it doesn't make sense. So don't just blindly do the state variables table. Look at the numbers and say, wait, does that make sense? Are my volumes, the correct order and placement in this scheme? And same with temperatures. The hot temperature is this isotherm. So this is T hot. Goodness gracious. Try it again. This pen's great when it works. And this is T cold. Those are isotherms. So this whole thing is the cold temperature. And this whole curve up here is the hot temperature. I've seen people mess that up too, and they'll put in the state variables table. Let me go back to one. They will have all of these temperatures shifted by 1. They'll have the hot temperatures here and the cold at the bottom and the top. And it's a total nightmare. All the numbers are wrong if you do that. So you just got to make sure it's more than just filling out the table. The table has to make sense. And if A to B is isothermal, they have to be at the same temperature. And if C and D are isothermal, they have to be at the same temperature. So there's lots of little places where you can go wrong. that shouldn't scare you. It should just mean that you got to do more than one of these problems to prepare for the test. It's got to be second nature. And that's the point I want you, and I always talk about the test, but my point is this calculation is such a foundational calculation for thermodynamics that you should be good with it. And so I'm just trying to get you to drill against it so that you can sit down and do one and not even worry about it. So let's dive in calculations. Okay. So first of all, we've got a problem. We've got our volumes in cubic inches. That stinks. What are we going to do about that? So we got to get out of our cubic inches. Let's write our values out here. So delta V is equal to 400 inches cubed. Compression ratio 8.38. That's unitless because it's a ratio. So that would be the max volume divided by the min volume, or the max pressure divided by the min pressure. T hot is 1780. And then the number of moles is equal to 0.050. So that's all we need to calculate all of the work and the heat and everything for this problem. So we need to know how much work is produced in kilojoules, how much heat's consumed, and what's the efficiency. So let's flip over to the video, and then we can work on all the different calculations. So what are we going to do about this cubic inches displacement?
Change it to cubic centimeters.
Yeah, okay, so that's good. So we're going to need inches cubed on the bottom and centimeters cubed on the top. And the inch is actually defined by the centimeter. Do you know what the definition is?
2.54.
Yeah, 2.54. Good job. 2.54 centimeters per inch. But this is cubed, so we cube that too. And so that will get us to centimeters cubed. And we want to get to liters, and so we need 1,000 of those. So 1,000 cubic centimeters per liter. We get the stickers ready because y'all may catch one of my mistakes. So I want you to be critical. We should get 6.555. We're going to write that in. Okay. Now we have that equation to use the delta V and RC to get VA. So VA so that's 6.555 liters over 8.3138 minus 1. Point what?
0.888 liters.
888? Okay, beautiful. And then delta V is VC minus VA, and so we can get that AC is, oh yeah, RC. RC is VC over VA, so RC times VA gives us VC. So 8.38 times the VA gives us VC.
1.44.
7.44. Let's just do everything in three significant figures.
7.441.
Okay. No, that's good.
Oh, okay.
And so we have our first two variables for the state variables table, and we have the temperatures. So let's go ahead and make our table. I'm going to erase this and put the table over to the left. And so we have our volumes, VA and VC, and then we can put our temperatures in. So where does the temperature hot go? On A and B, both. T hot. That was 17, what? 80. And 13, what?
50.
50. You can do everything in liters and Kelvin and atmospheres. There, put my units at the top. Okay, so we're off to a good start. We also know number of moles. I only put that on there. I mean, it's redundant. It's the same for all 4 points. But the thing is, you can look at it, and you can then see for PV equals nRT, we've got one unknown, and we have the gas law. So we can find the pressure for C. We can find the pressure for A. Okay. So let's do what we know. We can do that very easily. And so for this calculation here, let's do that. So it's the number of moles, gas constant, the hot temperature divided by VA. For a complete answer on the exam, I'd like to see all of the units. Doesn't take that much time to put them in, and then you can see them cancel, which is nice. Oh yeah, thank you.
Use another.
Woo! There's a sticker.
There should be.
206. And it should be liters, atmospheres. Yep. And that's why I said I've used the units, because those wouldn't have canceled. I would have had a joules up there and would have said, aha. So the moles cancel, Kelvin, liters, and we have atmospheres. This should be our highest pressure because it's the smallest volume and the highest temperature. So it should be 8.23 atmospheres. Who said that about this? Okay. Let's do C, PC. It's a colder temperature, so it's this, change this to C. Same number of moles, so we've got 1350, and then a different volume, 7.44. And so that's the lower temperature, the largest volume, so this should be the lowest pressure. And it's coming in on this chart at 0.74.
Yeah.
All right, so we're now stuck with using the ideal gas law. We can't go any further without the adiabatic relationships. So how are we going to get volume B and D? And so you got to know which ones are connected by adiabatic relationships. Okay, so that's when you go back to your mind and think about the cycle problem. So we're looking for B, and in that cycle problem, it goes A to B, that's an isotherm, and then B to C is an adiabat. So because B and C is an adiabat, we're going to use this volume here and these two temperatures to give us this. So we have the temperature drop from B to C, which is adiabatic, and we're going to have the volume expansion. And so we've got to figure out how to find this volume using those adiabatic relationships. So we would go to the notes or your note card and find what those relationships are. So we're looking for one that has volumes and temperatures. The two fractions with gamma, we need to know what those are. Okay, so dig through your notes and help me find out what relationships we have. We'd like to find like a VB over VC is equal to some relationship of temperature and then some relationship with gamma in the top.
TC over TB, and then the exponent will be 1 over gamma minus 1.
1 over gamma minus 1. Okay? So that's the adiabatic relationship. Can now the people confirm that the B's and C's are correct? Because that's where a common mistake is. It's easy to switch these two. And so you got to check your work to make sure you have the correct B's and C's on the volumes and the temperatures. So we've got our temperatures. We have 3 out of the 4 variables here, but we need to know gamma. And so in this case, we're talking about linear molecules. So gamma for a linear molecule, gamma is Cp over Cv. And so start with Cv for a linear molecule is 5/2 R. And then you add 2 more to that, 2 more halves, which is adding another unit of R to get Cp. So then 7/2 on top. And so the halves and the R's cancel, and that's 7/5. Can someone calculate that for me real quick, just to give me a decimal number, because I want to check it versus...
1.4.
Yeah, okay, that's what I have on my sheet. And so you could leave it in 7/2 and put it right here. 7/2 minus, what is 7/2 minus 5/2? 7/2 minus 1, right?
Yeah.
So that's going to be 2/2 on bottom, and 1 over 2 over 1 over 2/5. It's going to be 5 over 2. Okay. Do I need to do that by hand? So 1 over 7/5 minus 5 is equal to 1 over 2/5, which is equal to 5 over 2, which is equal to 2.5. So this exponent is 2.5. Is everybody cool with that? There's a lot of little quick things with fractions, but that should work. And so we just take our equation here, VB is equal to VC times TC over TB to the 2.5. Now, you may have to use that key on your calculator, the y to the x key. Okay, because you have to raise something to the 2.5 power. Okay, so let's put the numbers in there. BC is 7.44 liters. The temperature at C is the cold temperature, 1350 Kelvin. TB is the hot temperature, 1780 Kelvin, all raised to the 2.5. Any results from anyone? What do you have, Helen?
I have 3.736.
3?
3.7 or 73.
Yeah, 3.73, okay. Liters. Now we look at that and we do a quick check. Is it between VA and VC? And it is. So that's pretty good. If you had these temperatures swapped, this would be greater than 1 and it would be much higher than VC. So that would be a way to catch your work. You look at this number and you say, okay, it's between VA and VC. B should be. Okay. And so that comes in at 3.73 liters. Yeah, that's what I'm getting to. Good. Then we do the same relationship. We don't have to redo any of the exponents or anything like that. With just using A to get to D. Okay. So we've got different letters on there, but let's see if we can just write it out like we had before. So my B has now become D. So VD is equal to VA. And so since B has become D, then this is TD on bottom and TA on top to the 2.5. Does everybody agree with what I did? You could just see now, looking at those, B became D and C became A, the same relationship, because it's an adiabatic relationship. So, 0.888 liters. Temperature A is hot, 1780 Kelvin, 1350 Kelvin, 2.5. And this is going to be good. A is the smallest volume we have, and we're multiplying by a fraction that's greater than 1, and so that volume should increase.
1.77.
1.77
Yes.
liters. And that's good too. 1.77 is still between A and C. So that's how you use the adiabatic relationship. And you're done needing them because now we just have one variable that we're missing and we can use the ideal gas law. So you just have to use those adiabatic relationships twice. I typically use them to get the volumes and then calculate the pressures using the ideal gas law. So PB temperature for B is the hot temperature. And PB is 3.73 liters. So now we can calculate the pressure for B. You get 1.96. Okay. And then let's see who's fast. Have we got the pressure for D now?
3.13.
3.13. Okay, so there's our state variables table for this Carnot cycle that we have with a 400 cubic inch displacement, compression ratio of 8.38. So we now know what the maximum pressure is in our cylinder, 8.2 atmospheres, the minimum 0.74. That's actually accurate too in terms of a vacuum on some of these pistons. When they open that intake valve, it's less than less than 1 atmosphere. It's pulling a vacuum. So that's interesting. And then we have all of these variables now. We can calculate the different legs. So we can calculate the heat and work for leg 1 to 2, A to B, B to C, C to D, and D to A. So let's calculate, I would say, the performance variables. We've calculated the state variables, which tells us the state of the system. And now let's calculate the performance. How much work do we get out of each leg and everything? Let me get a new marker. So how much heat do we get from A to B? What's going on with A to B? That is an isothermal expansion. Okay. So isothermal, delta U is equal to 0. Q is equal to minus W. And so it actually makes more sense to calculate the work because we know that work equation. So W for an isothermal expansion,
Negative N.
yes,
T.
is equal to negative N RT natural log of V final. So if we're talking about our volumes, it would be VB, because it's right here, we're going from A to B, so VB over VA. Where do you think that you're going to mess that equation up if you were to make a mistake? What's that? Units of R, but see, if you hold on to your units and use them, then you'll catch yourself on that.
The negative.
Drop it to negative, and then I tend to screw up the volumes. I typically get those reversed. And so I've got to think about the leg is A is initial, B is final. So I'll put VB on top. Okay. I'm going to use 8.314 joules per mole Kelvin as my R because I want to get joules. This is at the hot temperature, 1780. That's another place where you could mess up. But if you've got that diagram in front of you, just always check your work in terms of the diagram. It's 3.73 for 0.88. Okay, so before we do the calculation, can we just look at this and see? We're going to get a positive log because it's greater than 1. Positive log, and we've got a negative sign here, so it's going to be negative, which is good. The system's doing work on the surroundings. That's a negative work. Anybody have a number for me?
Negative 0.597.
Negative 0.597 joules. My kelvins cancel, my moles cancel, so we've got joules. Anybody else confirm that?
I got a much larger number.
Yeah.
Negative 1,069.
1069, okay.
Yeah.
Okay, so we got a discrepancy. What do we think? What do you-
How close did you die? I got negative 1061.
Okay, so you can get to the top. Okay, so maybe a button error or something. Okay, all right, let's go with the 1069. That's what my spreadsheet got to. So I went ahead and made that a kilojoule. So 1.07 kilojoules. So let's make these kilojoules. 1.07 kilojoules.
Yeah, I did the natural log incorrectly.
Okay. Negative. And if it's negative 1.07 kilojoules for the work on the isothermal expansion, you change the sign and that's the heat. So plus 1.07 kilojoules. We had to put that heat in there to keep the same temperature. So there we're actually converting heat directly into work. Is it perfect? Probably not. That's the third law or second law of thermodynamics. But that's the isothermal expansion. So now let's do the next one. This would be the adiabatic expansion going from B to C. We're doing C, okay. All right, so B to C. We could actually, let's do C to D here and D to A. We know two of these values are 0. The adiabatic expansions and compressions, because it's adiabatic, you have 0 heat. Okay, so we could put 0 here and 0 there. Because they're adiabatic. And so how do we calculate the work? Well, we use the first law of thermodynamics. We have delta U is equal to Q plus W, and Q is 0. Okay, so delta U is equal to work in the adiabatic expansion, and so delta U is also equal to N CV TF minus TI. So we've got a change in temperature. N times the CV times the change in temperature. So let's calculate that. I'm going to go ahead and put in the 8.3. And so then T final, because we're going from B to C, final is 1350, and initial is 1780. So 1350 minus, that's Kelvin, minus 1780. And so that's a small number minus a large number, so we're going to get a negative number for our energy change. That's right, because we're dropping in temperature, and also that we're doing work.
Negative 146 joules.
Okay, so I'm going to put negative 0.44 kilojoules, okay, or 45. What about this equation down here will change for D to A, because that's an adiabatic exchange as well.
Temperature.
The only thing, you'll swap the temperatures, but the heat capacity stays the same, the number of moles stays the same. So it's the same calculation with just a change of sign. And so if this adiabatic expansion is a negative 45 kilojoules, this is going to be a positive 45 kilojoules. Makes sense? Okay, good. So then now we have just one more row to calculate in our performance table. just like we did for A to B, we're going to use that isothermal expansion. This time it's a compression, but it's that work is equal to minus nRT. And in this case, we're going from C to D. And so D is going to be our final volume, D over BC. Okay? And so we put in the numbers for that. You already calculated it?
Yeah, 8.09 again for kilojoules.
Okay, okay. So for kilojoules, 0.81 kilojoules. 0.809, yeah. Yeah, so it's 0.81. So that's going to be our work, and that's going to be positive, right? Because we had, BC was larger than, let's see, is that right? No, this was,
Going from C to D, so D over C, that's right.
yeah, okay. And so we end up with positive 0.81 kilojoules. And then because this is that isothermal compression, then the heat is just the minus sign of that. So negative 0.81. How does that work? Well, we're putting work into the system by compressing it, and that would typically heat it up. So in order to keep it isothermal, we have to sink that heat. So we have to take out 0.81 kilojoules if we're going to compress it at isothermal. So we're compressing it, putting in 0.81 kilojoules in the compression, and we're sinking out that same amount of heat to make it isothermal. So there's our performance table. And so we can calculate the heat in, Q in, and it's just the positive numbers in that column added together. So it's just one positive number, 1.07 kilojoules. Okay, and then we want to calculate work net. So it's the sum of all of these. So the 0.45s cancel, and so it's just the sum of 0.81 minus 1.07. So it'll be negative. So what do you get when you sum this column? Anybody?
Negative 0.0 or 0.26, rather.
Yes, negative 0.26.
Kilojoules. Okay. So this is the amount of heat we put in, and that's the net amount of work we got out. So we can calculate the efficiency using that. So the efficiency for the Carnot cycle, or for any engine, is equal to this absolute value of the net amount of work divided by the amount of heat you put in. So you put in a certain number of joules as heat, and you got a certain number of joules out. And so we don't want negative efficiencies. So we just change the sign and just calculate the magnitudes of the joules in and the joules out. So it's 0.26 over 1.07. It's close to 26, but at that 07, it gives us a little bit less. So it comes out to be about 24% efficient. Is that what you got?
Yes.
Yeah. 0.24. So 24% efficiency for this system. What do you get when you look at the temperatures? You get the same thing for the Carnot cycle. Is equal to 1 minus T cold over T hot.
So this engine was the most efficient it could have been.
Yes. Cool. And so we get the same number if we use the temperatures. So that tells us we did all of our expansions correct. We did all of our adiabatic relationships correct. Now we can't we can't do that for the Stirling engine because the Stirling engine's not a Carnot cycle.
Yeah.
So when we did the heat and work and all the expansions and stuff for the state variables table and then the performance values for the Stirling engine, we got 0.16 efficiency. And the temperatures in the Stirling engine that we used to fill out the state variables table, if it was a Carnot cycle, would have given 34% efficiency. So it's showing you how much we're really losing by not having those adiabatic and isothermal expansions and compressions in the Stirling engine. So if this engine, this automobile engine, were running like a Carnot cycle, it would be 24% efficient, which is really governed by the temperatures that you can have inside the engine. You change those temperatures, you change the efficiency. So, yeah. So that's the Carnot cycle. Any questions? It's doable. I mean, we didn't start right at the beginning of class, okay? But it's a long calculation, lots of places for error. But I would suggest you do 2 or 3 of these so that you're comfortable with them. And then when you're on the exam, you won't be panicked, right?
So we can for sure expect this problem.
Yeah, this is the problem because this is such a classic problem. I can't feel comfortable you graduating from the thermodynamics class and not being able to do the Carnot cycle from beginning to end.
Okay.
I mean, you got to be able to hammer through it. It's just heat and work and adiabatic relationships. There's a lot of great stuff buried in this kind of problem. So I really would like for you to be good with it. Yes?
For the work from C to D,
Yes?
how did we go to a positive value on the work?
Because we put an
VC and VD. So that it was, we're going to D from C, and D is smaller. So the fraction was less than 1.
Or
And because the fraction was less than 1, when you take the log, it's negative. And so then that kills the negative sign in front of work. Yeah. So the negative that cancels the original negative sign comes from the logarithm. And that's why you'll get the sign wrong if you get the volume wrong on top or bottom. Yeah. Excellent question.